Welcome to 2.4, Modeling with Quadratic Functions, Part 3. Real-life data that shows a quadratic relationship usually do not have constant second differences because the data are not exactly quadratic. Relationships that are approximately quadratic have second differences that are relatively close in value. Many technology tools have a quadratic regression feature that you can use to find a quadratic function that best models a set of data. So let's do example 4, using quadratic regression. The table shows fuel efficiencies of a vehicle at different speeds. Write a function that models the data. Use the model to approximate the optimal driving speed. If you notice the table, your x values do not go up by equal increments. It goes from 20 to 24, which is an increase of 4, and then it increases 6 from 24 to 30, and then it increases 6 more from 30 to 36, and then increases by 4. So there's not a consistent increase in your x values. So we cannot do what we did before and look at the differences and the first and second differences and see if they're even close. So that's not possible. So we need to go straight to graphing. We're going to graph these on Desmos. We start by adding a table. And we're going to type our values in. I'm going to pause recording while I type this in so you don't have to sit here and watch me do this. I have entered all the values in from the table into Desmos, and now I need to adjust my x-axis so I can see these points. Notice your x values go into the 70s, so we need to adjust our x-axis to include everything up to like about 70. Now the y values go up to about 25, so I need to adjust the y-axis till my points come in. So there is my graph. I'm just going to stretch it out so I can use as much of that as possible. And we notice that it looks like it's a parabola. It looks like it's in a parabolic shape, U-shape down. So we need to find the best model that approximates this. Now we could, if you did not have a calculator to do this, you can pick 3 points and do what we did for the last section. Do systems of equations and solve it. That's a good approximation. But when you want to find the best regression model, and that's what this is, the best model for the data, we need technology. So that's what we're going to do with the graphing calculator, with Desmos. There is a specific way we write these. I think we've done this together, so we'll see. First, you need to type in you need to reference your y column. Notice that this column says y1 at the top. So that's how we need to write it. We need to write y, and then you click on the 1, and it just puts it down there in the bottom. Then we need this little, I'm not sure what it's called. It's like a wiggly mark, but you go into your keyboard, your ABC, and down below the B and the N is a little squiggly mark. And you click on that. And that's going to tell Desmos you're going to do a regression. Now we need to type in the blank form of a quadratic equation. ax squared plus bx plus c. But it's not just any x values, it's the x values out of our table. And if you notice, our x values in our table are called x1. So that's how we're going to refer to them. So we're going to type in a, x, and then we're going to click on a 1 because it's x sub 1. And we're going to square it, plus b, I need to go grab a b, x sub 1, plus c. And that gives us the regression model. Notice your r squared value is 0.9992. Now, just like we did the linear regression models, when you looked at the R value, remember I told you the closer it was to 1 and 0, or 1 and -1, the better. The closer to 0, it's not a great model for that. Same idea about R squared, but R is only for linear equations. R squared, when you square that R value, it makes everything positive. It's the same R value. When you square it, it makes everything positive. So the closer that is to 1, the better that your regression equation predicts your data. So with an R squared value of 0.992, this is a pretty good fit. It's really, really close to 1. And notice how they give you the values for A, B, and C. So all we have to do is write this function. So let's do that. So our equation is, and they don't tell us what we have to, oh yeah, this is y equals A value. We look at our, we look right here. Here's your A value. It's negative 0.014. And I think that's all the decimal places we're going to use. Okay, so negative 0.014 x squared plus bx. So let's look for our b. Our b is right here. It's 1.366, and we'll stop there. So 1.366x plus our c value. Our c value is right there, negative 7.144. And we're just going to go with that. So negative, so it's minus 7.144. And that is the regression model. It fits our data. This was nice enough. The Desmos calculator was nice enough to graph it so we can see how well it fits the data. So we can use this to predict other values. So if we want to predict what the fuel efficiency for, let's see, 65, we don't have it at 65, for 65 miles per hour, we can plug 65 into our x values and solve that. Now we got to be careful. Our model was created for our data set. So when we look outside of that, outside of our data, so we say we went from 0 miles per hour, we plug it in, or we do like 150 miles per hour, which is way outside of our data set. That's called extrapolation. And when you go outside your data set, your model, it's not as reliable, okay, with the more extreme values. You stay within your data set, it's a good predictor. When you get outside your data set, especially if you go way too far outside your data set, it becomes less reliable. And that is all of lesson 2.4.